This is so much quicker when you got lecture notes written already. So I've got a challenge problem here. This is like I got it from the book. It's like there's a track and there's a railway where it's following a parabolic curve right there, but it flattens out. And at -10, the graph kind of changed, but it's a cart on wheels. And the cart needs to be, it's like a mine cart. It needs to be smooth. The ride needs to be smooth. You don't want it to fall off. It needs to be continuous. So continuous is easy to do. Differentiable is like where it's smooth. It's not like sharp corners or anything. But we don't know the value of B and C on our function right here for the parabolic one. So we're going to have f of x equals 1/10 x squared plus bx plus c when x is less than -10. That's what I was just doing right there. And then after it hits x equals -10, it just shifts to a flat line, -1/4 x plus 5/2. So for continuity, we need this side to match this side as we do the limits. So that's what we did here. I did the limit as x approaches -10 from the left. You plug the stuff in, you get that. The right side is where f is -10, and you just get 5. So f of -10 is 5. We're going to use that again in a second. You'll find when you clean this up, you get c equals 10b minus 5, which isn't enough on its own. But then we look at the derivative portion. This is where the differentiability kicks in. So we got to do our f of x minus f of a over x minus a. And we're showing the limit is the same on both sides. So on the right side is actually pretty quick. This is the f of x for the right side. This is the f of a. We clean this up. The right side gets down to -1/4. The left side, you got a lot of cleaning up to do. You're definitely going to want to pause this video and work this out, check it out. But we do have it here. When you get to here, you're going to want to factor this set separately from this set. And that's how we get this portion here and this portion here. And you eventually get it down to where the left side is b minus 2, the right side is -1/4. And we can solve for c. Now pause it for a second because I have a visitor. All right, we had a little more to cover, sorry. So we also have higher order derivatives here. Higher order derivatives, we've been taking the derivative. This derivative is called the first derivative. But later ones, we have like the second derivative, third derivative, stuff like that. And it's when we keep taking the derivative over and over and over again. The notation is on like here, we do more like we keep raising the apostrophe count. Goes up. But when you get to 4, you start putting it in parentheses. 4 and higher. We don't do like 4 slashes because then it starts to get unreasonable. Same thing with here. Leibniz notation actually never needs the parentheses because it's always done in a way where it's using numbers. So it's consistent. And like another way of writing this is doing like this part right here, ddx of dy dx. So let's just give you an example. Like we have f of x equals 3x squared minus 4x plus 2. We want to find the second derivative. We go through and here we're finding first derivative. All of this right here is find first derivative. So we go through and we use the limit rule, our limit definition, and we go through and find it, and we get 6x minus 4. You'll find out when you go through and do it yourself, you'll see that you get it. So that's where we start here, and then we're going to take the derivative of this. Take the derivative of first derivative to get second derivative. And so we call, say, f prime double prime of x equals the limit as h goes to 0. And now we're using the f prime here instead of the original function. And when you go through that, you'll get down to f double prime equals 6. Okay? Just make sure you take this patiently. Doing this part right here, a lot of students forget that this is x plus h times x plus h, and they screw up this portion right there. You got to distribute that right. Where this shows up an example in real life is position, velocity, and acceleration. The position vector is s of t. We've used that in our stuff before. The velocity vector is a change in position over a change in time. So this is like the first derivative of s. And then acceleration is a change in velocity over a change in time, which gives us the derivative of v, but the derivative of v is the second derivative of s. So as an example, let's say we have a position vector of t cubed meters. That's what the m is right there. This is m for meters. So we're going to find the acceleration function. If the position function is t cubed, find the acceleration function. And we got to use the limit rules, and we take it twice. So you go through and you'll get s prime of t equals our velocity. And our velocity, the derivative of t cubed is 3t squared. This is in meters per second because it's a velocity, whereas this was in terms of meters up top. And then when we do the acceleration vector, we're really doing, this is s double prime or v prime equals a of t. So we got to take the derivative of the last function we got. So derivative of this. So we use 3t squared there and there with the t plus h and then regular t. We work it out and we're going to get 6t meters per second squared. And that's an acceleration. That's our a of t. Okay, that's it for now. Peace.